Okay. Today, this is the first topic, modeling in the time domain. What's the meaning of the time domain? So what's your name? Obada. Obada. Obada. Just answer me. What is time domain? Yes. Yes. If you don't know, just say, I don't know. I want to know. Okay? Just say it. Okay? The time domain is basically just like that. It's related to time domain, but in control theory, we need to divide into two topics. Just remember the frequency domain, just previous week we have talked about it. And so in this week, we are prepared to study on the time domain or x dot, not just the s, complex variable or the Laplace variable. Okay? So in order to do that, we need to give the frequency approach limitations first, because if you want to understand everything about it, and so we need to compare it. Okay? Otherwise, we cannot know. And so, such as the frequency approach only applicable onto what? To a linear system. Because if you have the non-linear system, you can take the Laplace transformation, right? You know? Obada? Okay. And so, as well as this property, this one time invariant system, which means that we don't have the non-linearity, but just see that x dot is equal to the at xt. This is called the time variant, okay? Which means that the at is a function of the time. But in the Laplace domain, we can't apply the Laplace transformation on this system because it's in the form of the multiplication, guys. Okay? And so this results to the what? To limited applicability on the systems. Okay? So if this is true, and so instead of using frequency one, use, what's the meaning of the frequency one? Use yes, but with what? With Laplace transform, right? S domain. This is the time domain, and we have also an S domain, right? Okay? And so, just remember the system dynamic lesson. What's the meaning of the state space representation? Just say it. Huh? No, it's irrelevant. Not a metric. What is the state space? Yes, multiple input and output can be described by the equation of motion in terms of the what? Space. Which means that we should use the matrix. Okay? Just say. Okay. And so, if we have this property, instead of using the frequency one, we can model nonlinear system. Because nonlinear system can be represented by the time domain. Okay? Especially for the backlash. What's the meaning of the backlash, guy? Backlash. Saturation. Anyone knows that? Saturation. For example, if you have the motor, and so you can apply only positive 10 and negative 10 voltage to this motor. This is a saturation. We can't apply the 100 voltage. Okay? And as well as this DC motor, we have the system. For example, the mass spring damper or hydraulic system can have these bounds. We should call it the saturation. Okay? And also, in the frequency domain, we cannot use the initial condition. We cannot solve it. Okay? But in the time domain, initial condition feature can be given. Okay? With time varying system. Which is x dot at xt. Okay? This is a time varying system. The system parameter a is changing in time. Okay? So, just like what's your name? Burak. Just Burak said multi-input and multi-output. Right? These three features can be built on the what? On the time domain representation of the system dynamics. Okay? So, in order to do that, yes. Huh. I don't understand what you're saying. Feature. Yes. Okay. So, we need to define our solution process definition. We should follow these rules. Okay. Firstly, selecting a particular subset. What's the meaning of the subset? Anyone? Just remember the system dynamic lesson. We call it to the what? State variable. Right? For example, in a DC motor, we have two state variables, theta and theta dot. What is the meaning of the theta dot? What's your name? No. Yes. Huh? Pelin. Yes. What's the meaning of the theta and theta dot? Yes. So, this is the first step. In the second step, we need to write an TH order system as an simultaneous and first order differential equations guy. Okay? As state equation. So, just remember the state space representation. If we have the second order system, x dot dot or x dot dot dot, third order system, we can write everything in terms of the what? The first order one. Okay? This is a huge advantage for the what? The utilization of the state space representation, guys. Okay? And so, in the third place, giving n dash initial conditions to each state equation. What's the meaning of this? If we have theta dot dot, the acceleration of the DC motor, and so theta 0 and theta dot 0 should be given in this system. Otherwise, we cannot solve it. Okay? What? Which? This one. Yes. System as and simultaneous. Writing and th or I can fix this writing, guys. Okay. And so defining algebraic equation. Collected by state variables called output equation. These are the rules to what? To build our time domain representation of the R systems. But how we can do that? And so, in order to understand these terms, we need to solve the example, right? So, let's consider the system as just like this one. We have the spring, we have the damper, and mass. This is K, this is C, and xt is our variable, and ft is our input, right? So, in order to solve this, write firstly equation of motion. How can we do that? If we have these nominations, and so F is equals to the mx dot dot cx dot plus kx, right? This is true. Okay, and so just remember the previous peak in the frequency domain. If we take the Laplace transform of these terms, and so this can be written as fs s square m xs plus c s xs plus k xs. And so in order to create the R transfer function in here, and we can write this one, xs divided by fs. For a given force, how many or how much x deflect in time, right? But this is the representation of the frequency domain. And so, if this is the case, 1 divided by ms square plus cs plus k, right? This is the transfer function. So, but we have a problem. In here, we have the position deflection and the velocity change happens at the same time, right? And so, if we write the Vs for a given Fs, we should give this one. That's the R equation, right? Because S is a derivative term, and so if we multiply with the S, and so we will get the velocity. Otherwise, the position. But how we can write these two terms in one form? We want to know X and V, or the position and velocity at the same time. How we can do that? Obada. Obada mı, abada mı? Obada, okay. How we can do that? Nasıl yapacağız yani? Yes. Ben de sana sordum mesela. Okay, I'm a teacher, and so I can answer that. We need to use state space, right? So, the solution. In time domain, we need to define Dummy variable. What is dummy? Dummy, arbitrary number or variables, okay, or temporary. No, it's just like for example, in this case we have the state x in here. I can write the z as a dummy variable is represent the x, and so z2 is represent the x dot. I can do that. And so if we take the derivative of the z1, derivative of the z1 is equals to the what, Pelin? Yes, and yes, z2. And so z2 dot, which is equals to the what? And so, yes, but how we can do that? We have the equation of motion in here, guys, right? And so I can take or pull the x dot dot to be left alone at the left hand side, which is equals to z2 dot, and so I can write this one, f divided by m minus k divided by m z1 c divided by m z2. I can write it. Right? Yani ben bunu nereden yazdım? Bak buradaki denklemden yazdım. X dot dot'ı yalnız bıraktım burada. Okay. Answer. So we have the z1, z2, and z1 dot, z2 dot. Right? So we can write down as z vector, just like this one. z1 dot, z2 dot, right? And so we have the states z1 and z2, right? Plus we have also a force values in here. This is the input. Okay. And so what's the dimension of this matrix? This is 2 times 1. This is 2 times 1. This is 1 times 1. What's the dimension of this matrix? Huh? Yes, 2 times 2. And so what's the dimension of this matrix? No, 2 times 1. Okay. So we have 4 elements. We have what? 2 elements. And so what's the representation or the formula in equation of motion? Z1 dot. How can I fill these matrices? Z1 dot possess the Z1 or F. Is that true or not? Just go to the Z1 dot, which is equal to Z2. And so Z1 cannot include it in the what? Z1 dot. Or this is 0, right? And so F, we cannot have the F in here, and so this is also 0. But we have Z2 with the coefficients of the what? 1. And so how about the Z2 dot? Pelin. Yes. In this case, yes. And so in the second place, we have Z2, which is the coefficients of the Z2 in here. Yes. And so what is the coefficients of this term? F? 1 over m. That's true. Okay. And so in this case, we call it to the what? The state matrix. This is called, it's related to the input matrix. Right? Okay? This is the definition of the what are terms in here. So, in this case, we can write to this one in a vectorial form. Z dot, which is equal to the A, Z plus B, F. This is the representation of the what? State space form. Okay? You understand? Okay. So, in this form, we have the special names about. Okay? First of all, we need to write to this one. In this form, we have z dot a z plus b f. This is called the state equation. Okay? And also, this represents the system. If you want to take an output or give or feed the output to the outside, and so we need to give the y is a vector, output vector, c times z. Z is a state, just like in the DC motor. Theta and theta dot position and velocity value should be multiplied with the some matrices in here, and also d times u, or in this case f. But in general, we write the u and u in here. This is the output equation, guys. Okay? And also z is equals to the what? Z1 and Z2, and u in this case f, right? And also d is equals to the 1, and maybe c 0 1 in here. But in this case, just see that z dot is right from the previous slides. But if I choose the c 0 and 1 in here, what is the output? This is directly related to what the measurement of the R terms in here, okay? In the real implementation, this y is called to the what? To the measurement of your system. For example, in the DC motor, if you want to take the measurement from the theta, and so this c 1 and 0 should be written in here. But if you take the measurement of the velocity of this motor, and so this configuration is given in here, okay? And this d is equals to the 0, okay? Any question? You understand that? So, in this case, we need to conclude that the system can be iterable. What's the meaning of the iterable? Pelin. Huh? Iterable solution means that we can use the discrete methods to solve this equation, not the analytical one. Okay? Iterative methods can be used to solve the time domain response of this system. Okay? Which means that we don't need to use the solution of the analytical domain. We don't need to obtain the equation of xt or x dot t. We just solve based on this matrix formation. Anyone remembers the Ranch-Kata method, Euler difference equation method? Anyone? And so this system enables us to apply the Ranch-Kata methods, Euler methods, in a discrete form. Okay? This is called the difference equation. And so in the MATLAB, we can build this system and iterate it through a time. Okay? So in the second place, NTH degraded to the what? To first order. See, this is a vector matrix, but this is a first order. The first order is beautiful for us to solve any equation, even if it's linear or non-linear, guys. Okay? Everything is okay in the first order. Yani her şey harika yani. Anladınız mı? Oraya getirdiniz mi müthiş bir şey. So, if we have this property, we can combine two separate systems into one. For example, just remember the previous section, previous week, DC motor and mechanical system can be combined in frequency domain. But in this case, we can create the more state variable to represent the what? The electrical current is a state variable. For example, position of the DC motor or velocity of the DC motor or the voltage level of the DC motor can be represented by the states in one form. Okay? So, any question? Şimdi bir kere daha Türkçe geçeceğim üstünden arkadaşlar. Bizim geçen hafta uğraştığımız sistemde değerler ders sistemi vardı. Biz bunu ne yapıyorduk? Equation of motion'unu çıkarıyorduk. Çıkardık mı? Laplace'dan sonra biz bunu yapabiliyoruz değil mi? Aldık bunu neyse. Bunu çözdürebilirsiniz, çıkarabilirsiniz. Ancak bizim burada şöyle bir sorun var. Birincisi bu lineer olmayabilir. İkincisi time'lerin yani sistemin parametreleri zamanla değişebilir. Üçüncüsü sizin bunu çözmeniz analitik olarak çok zor olabilir. Bu zaman biz ne yapıyoruz? Hemen gidiyoruz. Bir tam bir ya rastgele bir değişken tanımlıyoruz. Z1, Z2. Birine x, birine de x tanım. Bak biri first order, biri zero order. Değil mi? Sonra gidiyorum ben bunun türevini alıyorum. Ben bu otomatik formunu oluşturduğumda bu x, x dot, x dot dot, x dot dot bakın hepsi bir vektör halinde tek bir forma geliyor. Şimdi bu bana ne sağlıyor? Şunu sağlıyor. Ben artık bu matrisleri ve bir sonraki adımını bildiğim için bunu zaman içerisinde çözebiliyorum. İtererek. İlk adımı sıfır anında çözdüm. Sonra birinci an, ikinci an, üçüncü an, dördüncü an. Bunları ne yapabiliyorum? Sıra sıra böyle itire son değere ulaşabiliyorum. Frekans domaininde bunu yapma şansınız çok yok. Çünkü düşünün 8 tane denklem vardı, 8 tane domain birbirine bağlı. Nasıl çözeceksiniz? Çözemezsiniz. O yüzden bizim bu state space dediğim şey ne? Z eşittir AZ artı BU. Y de buradaki ölçüm vektörümüz. Sizin sisteminiz var mesela. C'yi 0'a 1 koydum ben. Bu neyi ölçüyor? Z, Z1 ile Z2 olduğu için 0 ile 1 ile çarpıp sadece Z2 kalıyor. Yani bu sistemden sadece hız değeri ölçülüyor şu anda. Anladınız mı? Tamam mı? Okay. So, if this is the case, and so we need to write to example. If you want to understand anything, we should solve examples. Otherwise, we cannot learn it. So, just remember these properties in here, just like this one. We have the K1 C in here, K1 C1 M1, and also we have another spring element in here and ampere and M2, right? And so this is the FT, and so we have the M1 and M2 in here, K2 C2, and so this is the X1, this is the X2, and so our question is that drive the L, right? This is the case. So how can we solve this formulation? This is so important because in every system we have just kind of free body diagrams or the analogy. Okay, and so I need to teach you how you can handle this problem in a rules. Okay, so first of all, you should write this one, and so these are the problem. Solve, and so 1. In the first place, you should write the free body diagram. F, B, D, 1. Using Newton's law. So, the M2 is given in here. And so, X2 is defined in the direction of the down in here. And so, F pulls to the down. And so, what if I pull to M2 down? How the reaction force of the K2 and C2 happens in here? Yes, in the reverse direction, right? And so we need to draw this one. Okay, we have two forces, which one of them is induced from the spring, the other one is induced from the damper, right? And so how we can write this force? This force is the input, but how can I write the force of these terms in here? Just remember the spring rule. K2 times X, but in this case, we have a moving object, X1, right? And so if I pull the X2, and so the X1 is also moving down, right? But yes, X2 minus X1. What about the C2? C2 times X dot, right? And so, what is it, Pelin? X2 dot X1, right? Okay. And so, Burak, just say it. What is the Newton's law? Newton's third law. Yeah? F equals M times A. Okay. And so we have the forces collected or induced from the tree of one, K, C, and input F. Okay, in order to use the Newton's law in here, I just write to what? M2 X2 dot dot. Okay, equals to the, what? The total F. So, just help me, Burak, in order to write the right hand side of these terms. Okay, first of all, F is applied in here. F is the positive of negative in here. Why? Because the direction is the same. Okay. F. What is the direction of the K2 in here? Yes, minus K2 X2 X1. What is the direction of the C2? Yes, minus C2 X2 dot X1 dot. Okay? This is the what? The first equation. And the second one, just write free body diagram 2. Okay? Again, the Newton's law gives us to this rule, but we need to use or create what? A free body diagram. Okay? And so, in order to write the free body diagram, we should put the mass in here. M1. X1 is in the direction of the down, right? And so, what is the force acting on this M1 right now? If I pull the M1 to the down, and so this K1 and C1 resist, right? Okay, we have two forces in here. What about this one? This K2 and C2 resist or not? If I pull, resist. And so, if the resist, what's the direction of this one? Up. Okay. See? That's simple. That's yes. K1. What's the K1 in here? K1 times X1 minus 0. Because it's fixed. Right? And so C1 times Yes, minus 0. And so, what about the K2? K2 times, yes, and C2, yes, thank you. So, Burak, we should write the Newton law or apply the Newton law, and we should get the equation of motion. So I'm starting to what? M1 dot x1 dot dot, which is equals to the what? First of all, K1. What's the, yes, minus K1 x1 and, yes, K1 x1 dot, and minus, yes, and so, that's all. See, this is the what? The complex representation of the what? The mass breakdown per system. But if you follow these rules, you can solve any system based on this one. Okay? Yes. Because anyone knows? The x1 and x2 are the deflection rate from given position. Okay? This is a rate. Delta x is equal to the x1 in here. Okay? If you give this m1 and m2 in this representation, and so this gravity factor pulls the k1 and k2 in here. Okay? And so if you want to create the dynamics of these terms, and so this g factor or the gravity factor should be removed. Okay? So so let's take a break for 10 minutes. After that, we will continue.